All right. Everybody say hi.
Hello.
Hi.
See? But now, you won't have to watch this one. Hey. Good morning. All right, so has everybody been watching, keeping up? I posted late Friday. I apologize for that. Because I was like, I'm not sure, my timing-wise, to have this ready for you by 9 a.m., which would be kind of nice for schedule. And I'm not sure how to live stream. I think I can do that on YouTube, but I'm not sure if we have enough bandwidth to do that. So I'll just sit there and look at myself. I got a haircut on Wednesday, and I think you and Wednesday you're the only ones that know it, because Friday they didn't know it. And with masks on, I can't tell who anybody is at all. Who are you people? Was there anybody who's here today that wasn't here on Monday? Good, because I wouldn't know what to do. I think that's the syllabus and things. But so we've been covering some ideas of bonds and bond strength as the kind of critical thing, and talking a little bit about real basic chemistry, which is in part going to flavor our entire discussion that we're about to get into in terms of macromolecules. And I thought, just to review here, as we're saying, we got covalent, which, short of some kind of enzymatic process, it looks like it's backwards to me, but oh gosh. It must be videoing it, though, forwards. Tell me it is. If I lecture for an entire hour and it's backwards, how embarrassing is that going to be? It can't be. Someone tell me there's not. There's videoing.
For
The
ours that we
videos
saw,
were
it was fine.
regular.
I know, but I have it set that way sometimes. And see, I'm sitting here talking. Skip over this part. We'll try it, see. There's a little mirror image flip that I think shows me what I'm doing, but it's always recording straight up. You never want to record mirror image. That's just stupid. I don't understand this. Like, cameras don't do that. Regardless, covalent bonds, strongest bond. So enzymatically, we can break covalent bonds, yes, but short of using enzymes, which we'll get into and how they work, covalent bonds, pretty much for biochemistry, the only way we're going to break these guys is fire. Fire. The only way we're going to break them is by burning it. So 450 degrees. The point being that under normal biochemical situations, you're never going to find yourself above, 120 degrees, the highest point on the planet, other than like a volcanic vent or something. All right, covalent bonds are not being broken in sort of normal biochemistry. Then we've got, significantly weaker in water anyway, ionic bonds. These are a lot weaker. And then we finished up with my favorite, sort of the Velcro of the biochemistry world, the hydrogen bond. And we can then throw in sort of the, I think the catch-all for chemists, van der Waals forces. So pretty much the answer to anything is going to be hydrogen bonds, but if that's not the right answer, then van der Waals forces is probably it. Van der Waals forces are things that happen when molecules and atoms are very, very close together. And I would never write down my definition of van der Waals forces because I don't really know what they are. But we can think of things like polar, nonpolar interactions as other kinds of, not bonds, but organizing energies and things. And so, oil and water don't mix. And we'll be kind of bringing these kinds of ideas into play as we start talking about our macromolecules. Another thing that I thought we should probably do is, how many of you are, or who is not in organic chemistry? Everybody's in, or have you had organic chemistry?
I had the first
Yeah.
half of it, but I'm not doing the second half.
Okay, how about you? Have you had any at all? No problem. I can tell you everything you need to know about organic chemistry, a 2-semester class. We can summarize it in probably 5 minutes. Organic, hey. Number one, we're talking about carbon. And carbon always is going to have 4 bonds. It can have double bonds, but it always has 4 lines coming off of it, the way at least I draw it. I don't draw those little squiggly structures. Can you even see that carbon? I don't even know where it is. Yeah, whatever. So There are a couple of things that make carbon molecules interesting. First off, just a brief nomenclature. One carbon is the methyl group. It's also known as our formal or formic group. So we have things like formic acid or formaldehyde, one carbon. Two carbons is the ethyl group, but often in the organic chemistry biz, we'll see this as the acetyl. There's an acetyl group, like acetic acid is a two-carbon acid. We'll talk about acetates groups, or acetyl-CoA is a two-carbon molecule that we talk about in metabolism. So there you go. This is pretty much where our nomenclature is critical. Three carbons, just to throw it out, is the propyl group, and things like propane and isopropyl alcohol. A good hand sanitizer, although you can't eat it, or you shouldn't anyway. And then four carbons is the butyl group, or butane. Again, just some interesting little bits. And so one of the things that is important about organic chemistry to recognize is the periodicity of it, or the predictability of it. As we add more carbons, we begin to lower and lower and lower, we begin to raise the boiling point. And so, we begin to raise the boiling point, meaning that methane and ethane are gases everywhere on the planet, propane too. But this is a little interesting fun fact. Butane is, in fact, got a boiling point of somewhere around 24 degrees Fahrenheit, which means that potentially right now, if you were to crack open your butane lighter, you could pour the butane into a little cup, and if you put your hand in it or put your hand around it, put your finger in it, it would begin to boil off. But it actually is liquid at really cold temperatures that we might be able to see here. These other guys, they're always gases. And it's one of the things that you can begin to predict about organic molecules is whether they're going to be in a liquid state or a gaseous state based on, the temperatures and things. We're talking about biochemical type temperatures. And butane, you might find that actually as a liquid. You get into five carbons, and it's one of the things that I always think I should look up. Pentane has a boiling point of rats. I don't know exactly, but it's probably somewhere in the 40s and 50s. I know that once you get up to six carbons, so this is five, hexane we got in a bottle, just sitting around the shelf. So as we add more carbons, we begin to make a bigger molecule, lower the boiling point. It's not nearly as volatile, and they're all quite flammable, quite delightful. Now, the other critical point to thinking about organic chemistry, there's the idea that you can have double bonds. So I didn't throw that out, but there you go. The other part of organic chemistry that's important is the functional side groups. And there are a bunch of different functional side groups that we can talk about in organic chemistry, but for our purposes, we really just have a few. We have the alcohol functional side group, which would be the OH group. And so what we've drawn here is a one carbon methyl alcohol. This is methanol, also known as wood alcohol. Microorganisms, bacteria, not yeast primarily, will convert carbon into one carbon methyl alcohol. In the body, it gets converted into formaldehyde, which you don't need to know the structure, but just say we did. Formaldehyde is embalming fluid. It is something that actually is able to fix membranes and essentially cross-links them. And your eyeballs are particularly sensitive to formaldehyde. So apparently it is the number one cause of induced blindness in that you don't want to drink methanol. There's a whole notion that when people are making moonshine, that you should be careful about it because if you were to drink it, you might go blind. Unless you're generating a fermentation product that would be so incredibly nasty, bacterial infested yuck. Like you're going, honey, I ain't drinking this shit, no way. There's no way that you're going to get methanol in some kind of fermentation process, making your own alcohol. The only way that happens is somebody's intentionally adding methanol to be mean. So, that's one thing you don't have to worry about. That said, though, if you're wandering around at Lowe's and you see methanol, don't drink it. Now, that's the alcohol functional group. Just a little thought, when we have the OH, we do have the possibility of slight hydrogen bonding. So the hydrogen has a slight positive charge, the oxygen has a slight negative charge. Now, the next functional group on our hit list is the organic acid, the carboxylic acid group. And that is an alcohol with an oxygen double bond to it. And if we just throw in a hydrogen here, we've made one carbon acid, formic acid, apparently the active ingredient in ant bites. We don't typically consume formic acid, but it certainly is something that you could eat. And if we throw another carbon on here and put the hydrogens appropriately, we now have made, but you would think it'd be nice if they called it ethyl acid or something, but this is acetic acid. This is vinegar when you dilute it down to 5%. All right, so there we go. Just in terms of acid-base chemistry, this is a hydrogen that dissociates. All right, in addition to the carboxylic acid, we have sort of the organic form of the base, an amine group, which is simply a nitrogen, and depending on the pH, you can have 2, maybe 3 hydrogens on it, and we can produce different kinds of organic molecules with the amine group. Here we're beginning to draw cyanide, but I'm not going to get into it. All right, so that's the amine group. Alcohol, carboxylic acid, amine, and you pretty much just have to memorize the structures and know that when we say, okay, here's the carboxylic acid, or this is the carboxy terminus of a protein, we're talking about the carboxylic acid, and the amino terminus, we're talking about the amine. Lastly, another sort of functional side group that maybe not always thrown in organic chemistry, but really critical in biochemistry, and that is the idea of the phosphate group. Phosphate. And this has been my mantra for several years now once I began really thinking about how energy is transferred in biochemistry. The phosphate has got a gigantic stinking negative charge. And so there are very few things that I'll ask you to either write in Sharpie on your forehead backwards, so when you get up in the morning you read it in the mirror, or if you really are into this, go ahead and get it tattooed. But this is one of them. I mean, leave some space because there's a few. And that is, whenever you see phosphate, you must immediately think to yourself, negative charge. So when I say phosphate, you think?
Negative charge.
Brilliant, thank you. All right. You might find this to be trivial and amusing, but the fact is, this is the shiz. This is what makes energy drive. It's what makes our muscles contract. It is what is doing all the heavy lifting in biochemistry. It's the ability to take a phosphate, put it on, change the charge dramatically, and then we have the ability to pull it off. And as we get further into this game, we'll start seeing later in the semester, one of the really cool topics we'll talk about is hormone signaling. And hormone signaling, and it turns out cancer, all involve phosphates. You cannot overemphasize the criticality of phosphorylation. This is what drives the whole show. And it's because we have this massive negative charge. Okay, so that is what we had to say about some of the basic chemistry. And I'm looking here in chapter 2 and just flipping through to see if there's anything else I want to say. In terms of the periodic table, there's 110 elements. We don't need half of them. We don't even need 3/4 of them. We got calcium, magnesium, phosphorus, sodium, potassium, and the rest of them, forget about it. Yeah, iron, sure. We have trace minerals within us, but those are the biggies. So you don't need to know your whole periodic chart. Forget that. All right. So now, the next step in sort of establishing the base groundwork for our discussion is thinking about how we can build biochemical molecules. And when we start thinking about biochemistry from this next level, it's all about polymers. That's really what everything comes down to. And we see polymers in our everyday world. So a polymer, just to define it, a polymer is made up of a whole ton of smaller molecules known as monomers. So it's a whole series of repeating subunits, the monomer. And so when we start talking about polymers, the way to really think about them is, what is the polymer and what are the monomers that make it up? And that's what we're about to do. So in terms of just thinking about polymers and monomers, we can point to examples all around the room of any kind of polyethylene, polystyrene, polypropylene. These are polymers. These are plastics. And so you have your plastic 1, 2, 3, BPA-free, high density polypropylene or low density polypropylene, and saran wrap. So they're all polymers that are primarily petroleum-based, synthetically produced, but we've got a whole bunch of polymers in things like starch and pretty much every interesting biomolecule. So that's our next really big chart that we want to start building. And probably going to be like the first question on the exam, worth 15 points. What are the biopolymers? What makes them up? And what is some interesting things about them? So there we go. And that's what we're going to do, is we're going to just start building this chart. And from a food perspective, it more or less is what the biochemist would think of as the actual food groups. So let's start. We've got carbohydrates. We have fats and lipids. We've got proteins, and we have nucleic acids. These are our 4 biopolymers. Meet your 4 biopolymers. And they each would step out and say, "Hi, I'm carbohydrate." And then I think of something that would look like Jabba the Hutt comes out and says, "I'm lipid." I don't know, it's fat, whatever. And then proteins are going to be dancing, and then nucleic acids are more like ballerinas, I would think. That was just my imagery right there. Take it for whatever it's worth. All right, so in a quick nutshell, we're going to go through each one of them, but in a quick nutshell, the monomers that make them up are sugars or monosaccharides. For lipids, the lipid class doesn't fit into the monomer-polymer model nearly as well, but we throw it in here, and we're going to talk about it, but we'll see it's a bit more complicated. The base sort of molecule for our chart anyway, we'll say is the fatty acid. For proteins, it of course is the amino acid. And for nucleic acids, it is the nucleotide, or the nucleic acid. So, we got sugars, fatty acids, amino acids, and nucleotides. And using these molecules, we're going to start building really big stuff. And we can kind of mix and match. We can have mixes with sugars and fats and make lipopolysaccharides. Certainly, a lot of proteins will often have a bunch of sugars, a glycosylated protein. Nucleotides are everywhere, DNA, RNA. We start talking about ATP, the energy currency of the cell, blah, blah, blah. It's a nucleotide. All right, so now we'll erase that and start from the top. And when we go look at the book here, and it's one of the things I kind of go, not the best organization, but chapter 4 is devoted to protein structure and function because it's like a critical thing. We will probably pick up a lot of the protein structure and function component when we hit the amino acid polymers, just because it fits well there. But we'll also kind of touch on chapter 4 as well as a separate little bit. Anyway, carbohydrates. If I was to say, what's my favorite biopolymer, sure, it's carbohydrates. Sugars. And by far, the number one sugar is the 6-carbon glucose. One of the things I hate about this thing being videotaped is that it's here potentially for posterity. And I used to say to myself, I'm going to memorize one structure every semester. And I'm trying to see if I can think about what glucose is and draw it for you. And I'm embarrassed on tape to say, I don't know that I could draw it for you exactly. Yeah, that's what I thought it was. Okay, I can. But I was like, do I know it? I think so. Regardless, it is a 6-carbon molecule. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. And it has got a double bond oxygen up here, but everywhere else it's got OHs on it. And there's probably some sort of stereochemistry that I'm screwing up. But for my purposes, I just don't care, okay? I don't care. And, so when you take biochemistry and you memorize the structure exactly, bully for you. It is a stereoisomer, whatever. And normally, in solution, you take glucose as this 6-carbon molecule, it cyclizes, and it forms a hexagonal ring where you have an oxygen link, and I can't draw it. I don't know how to draw it. All right, I'm going to edit this, and I'm just going to remove that part. Look it up. No. I can do it. I have the book in front of me. I screwed it up because I was drawing the pentose structure. How's it look? Yeah, that's how it looks. All right. If you guys have probably had this inorganic yet, or maybe you will. And, all right, so that's how it looks. And then there's OHs coming off. And, it's like the stereochemistry boat structure and all this, whatever. The OHs stick out in different directions. And if I really was concerned about it, I'd put it up, as a figure in PowerPoint. But I'm not. The main thing is a bunch of OHs, and it forms a ring. Great. Now, when we are going to polymerize this, we're going to take a OH group and link it together with another OH. We're going to make a molecule of water. You end up making an oxygen link between another sugar molecule. And really, don't worry about this, please. This is not the critical part. So we got the CH2OH up here. The point is, we can begin making glucose polymers. Another critical point is that we can either have this, literally, it looks like a zig or a zag. It's up or down. It's called the alpha 1,4 linkage, or it can be the beta linkage. And that has to do with the stereochemistry of how this oxygen is arranged in space. The critical point of this is we've got two really big glucose polymers that we will continue to talk about when you're thinking about sugars and things. We've got amylose, which is known as, of course, starch. And we've got cellulose, which, of course, is a chunk of wood. Now, this is one of the things that we can say, okay, a key point in biochemistry, is that starch and cellulose are both glucose polymers, identical glucose polymers. And truthfully, without really staring at it, it's not really obvious the difference. I mean, it is this zig versus a zag in the way the sugars are linked up. But if you didn't know this, let me clue you in. You can break down starch really, really well. You have the enzyme amylase in your saliva, and you can break down starch even before it is going into your stomach. The old 5th grade science trick of where you take a cracker or a piece of white bread and you stick it in your mouth and you sit there and slobber on it for a while. Just hold it for a bit. And after, 3 or 4 minutes, 5 minutes of holding this piece of Ritz cracker or saltine cracker in your mouth, you go, ooh, it begins to taste sweet. What's happening is the amylase in your saliva is breaking down glucose and popping the glucose off. Now, when you digest it, you get it in your stomach, man, it gets broken down really fast, which is why I think, at least from my food perspective, white flour is basically the same thing as white sugar. And the caveat is I have all this really wonderful nutrition advice. I never follow it, but I do know, that there's really no difference. And so when you're thinking about a bagel versus a Krispy Kreme donut, it's no question, go for the donut. Now, people would say, oh, I'm being virtuous, I'm having a bagel. Yeah, whatever. By the time it hits your stomach, it is converted into sugar so fast that your blood glucose rises not any slower than it does with that Krispy Kreme donut. Eat a donut. That said, my actual diet that I've been working on is my pixie stick diet. So you just skip the middleman. No polymers. Just take straight glucose. Try it. Glucose actually is kind of a fun sugar to play with. And last spring, I actually did an entire pixie stick sort of lab-grown pixie stick experiment. We'll get into that later. And one of the things is that sucrose, which we think of as as sugar, this is white sugar, table sugar, is a glucose and a fructose molecule. It is a disaccharide. Straight glucose isn't as sweet. And so, just not to belabor the point, but sweet is really just a nervous system neurochemical interaction sensation. And that's why you can actually spoof your tongue and have artificial sweeteners that are, completely weird-ass foreign molecules. I mean, some of them are made actually from, coal tar. And it tastes sweet. All you're doing is just binding to receptors on your tongue. It has nothing to do with the biochemistry of it. So different molecules bind to those receptors at different levels, and they taste really sweet or, wow, that's really, really sweet. And a lot of artificial sweeteners are like hundreds to almost 1,000 times sweeter than sugar. And so they end up having to dilute them down with various powders because you couldn't eat a spoonful of straight aspartame without gagging. So if you haven't tried a spoonful of sugar, which purportedly helps the medicine go down, that's fairly sweet. And it wouldn't make the best pixie stick. But if you take a spoonful of glucose, which I got upstairs, you can probably get it on Amazon, but you're not going to find it at the Kroger. Glucose is not nearly as sweet. Just a little point there. But glucose is the base sugar that we build all these different things off of. Now, amylose, we can break it down really well, really fast. Cellulose I will just tell you, you can now take the experiment where you had the saltine or the cracker and you crunch it up in your mouth and you hold it for a while. Now give your roommate a twig and have him chew that up, or okay, sawdust, whatever, and hold that in your mouth for a while and see how that tastes. Even after 5 minutes, it's going to taste like a mouthful of wood, because the biochemistry requires enzymes to break the sugars down, and our enzymes, amylose is broken down by amylase, cellulose is being broken down by cellulase. We don't produce cellulase, and in fact, I don't think any, no animals do. Fungi do, lots of bacteria do, and so the ability to break down cellulose is something that we absolutely don't have. And just as a little minor point, I'm always looking for new genes that I'm going to add into my super soldier, sort of as when the Clone Wars started up, or my augments, for those of you that watch your Star Trek. I'm going to for sure bring in the ability to generate your own vitamin C. I think that's going to have a really big effect. There's a couple of neurotransmitter tweaks that we'll talk about later. But I'm thinking also that if you had the ability to break down cellulose, you could feed your army on grass and sticks. And so like when, emergency rations, nah, man, you just sit there and just start gnawing on a stick. All right. Cows can do it, and it's not easy. Wood is a fairly tough biomolecule, as it turns out, but you can break it down. All right. Now, the real critical point, though, behind carbohydrates is when we put them into polymers. And this is an example here. A glucose polymer that we can digest, and that would be starch. And a really easy way to get this is from corn. So we've got cornstarch, and just for comparison, we have various kinds of flours. Wheat flour being a great one, mainly because the way agriculture has worked and over the millennia, the breeding of wheat to have lots of starch in it. It has some really important properties when you grind it really, really fine. And the same with cornstarch. But cornstarch does a better job for making pudding, but you can do the same thing with flour. And we're actually looking at our macaroni and cheese recipe today. Particularly this week, we're going to have macaroni and cheese. And we start out making a bechamel, or a white sauce, in which you take flour and butter, and then you mix in milk. And has anybody within the audience ever made a bechamel, or a white sauce, or a gravy?
My mom has, like, she cooks a whole lot.
You have? All right, good. I am fascinated by doing these things, and this is one of those cases where I wish I had my stove and the mirror that was kind of angled over, because we make a little macaroni and cheese right here. So you take butter, you take flour, like a tablespoon of each, you mix them over the heat, and you get kind of a gloppy mess. If you let it really toast down, it's called a roux, quite flavorful. You then take about a cup and a half of milk and pour that in. And you sit there and start stirring it. Now, when you add this, the milk, man, is going to just disperse the flour, and it is a very thin solution, and you're going, oh, this is not going to be good. Another example would be cornstarch and milk, and we're going to make pudding. And so you're stirring it, and you're going, this is not making pudding. This is like, I don't know what. And you can add some flavors and things. But once it turns, right before it begins to boil, the viscosity of this magically changes. And you can see that there's lines where your whisk is drawing through the fluid. And it is absolutely magical, if you like pudding anyway it is. And then when it cools, it really thickens. And here is what's happening. We've got these carbohydrate polymers, starches, glucose polymers. I mean, it is glucose as far as the eye can see. Literally tens of thousands of glucose molecules. And you can have branch chain starches and things like that. But mainly, I think about it when you pour the starch from the jar, or scoop it out of the container, it is like a bunch of balls of string or yarn all balled up. individual blobs of strain. Because remember, we've got all of these sugars, and they all have lots of OHs, and that means the ability to hydrogen bond. And so what you got here is a gigantic long chain of glucose that's all tangled up around itself, and it is in fact hydrogen bonded within the individual molecules, what we might call intramolecular hydrogen bonds. All right, so how do we break a hydrogen bond? And there's probably an amusing joke there, but I don't know. We break hydrogen bonds most easily by heating them up. And you don't got to heat it up too high, but for my purposes, you bring it to a boil, and you're guaranteed to have broken every hydrogen bond in that big starch polymer. So we add heat. Let's see, can I stay on the board? Let's put some heat here. Red for heat. And is there a room? Good. When you add heat, we're going to break the hydrogen bonds, and we end up with this kind of look. These really long polymers all now unwinding. And so what happens is that as you're whisking this thing up, the viscosity dramatically changes. You drew that so neatly. For a second I thought maybe you'd pull that in, and you print so well.
Thank you.
Wow. Well, let's talk about that. All right. So you go from individual balls to now these long strings. So you can think of this sort of like a knitting project where you got all your little balls of yarn, and now the cat comes in and opens them all up. All right. It's going to change the viscosity. But even more importantly is now once it cools, what happens is we go from having intramolecular hydrogen bonding to forming hydrogen bonds between the strands. We make intermolecular hydrogen bonds. And that means that as this stuff cools, it forms a gel. Yay! We've made pudding. And this is the same thing with making Jell-O. You can make Jell-O the same way. Jell-O, as we'll see later in the semester, or gelatin as we might call it, is in fact a proteoglycan, where it's got a small amount of protein in it as well. And this is the basics behind every kind of pudding and thickener that you're ever going to come across. So you now know the biochemical mechanism behind pudding. It is the intramolecular hydrogen bonding. Heat opens everything up, and then when you cool it, you have the intermolecular hydrogen bonding. I love pudding. And not surprisingly, I've carried out a not insignificant amount of research on pudding. You have, if you go to the grocery store and read your labels, you've got the pudding snacks that are in the refrigerator. And they're made with starch and milk and whatever flavorings. But you also, if you're carefully noticing, you have your pudding snacks that are not in the refrigerator. And they are actually biochemically distinct. They're made with a different polymer because it's the same thing with Jell-Os. You have your refrigerator Jell-Os, which are made with gelatin, and then you have similar label, but not refrigerated, and they're not actually made with gelatin. They're made with a different kind of gel because cornstarch-based things, they really need to be cold in order to keep their pudding-like behavior. And certainly, Jell-O, if you keep it at room temperature, it begins to dissociate, and it's not going to be nearly as gelled. So you have more of a gummy bear type thing for your shelf-stable, non-refrigerated Jell-Os. Well, we use these long-chain carbohydrates, to make pudding, obviously, but also they are responsible for various kinds of fluids in your joints. so they keep your bones from grinding on each other. Anytime we need to have something that's going to carry a lot of water, like the padding under your skin, all kinds of different molecules will have lots of sugars because they can form these gels, they can interact with water a lot, all kinds of stuff happen. All right, so just one little final point, because I make Jell-O, at least biochemically, for the food class routinely. You can get Jell-O to go into solution by taking, like gelatin, a packet, putting it into water, into, not hot water, but just tap water, and stirring it up. And you can make a uniform solution that won't fall out of solution, and it is thick, but it is not gelled at all, totally pourable. The only way you can get gelatin to actually turn into a gel is you got to heat it up. And in fact, if you don't heat it up enough, it still won't gel. Just a little minor point. See, biochemistry, everywhere you look, we're doing these things. All right. There's probably some critical things that I'm forgetting because I'm waxing on about pudding, and I really would love to have some pudding right now. But we'll move on. And, all right. So somewhere along the line, last fall, I kind of tweaked my right shoulder, and I train doctors. I teach, MCAT review. I have taught doctors. There's doctors in this city that, have had cell biology from me. I rarely go to them. And it's like, oh God, and trying to erase the board with my right arm sometimes is a little odd. And I'm just like working my way through it, just playing through it. Regardless, I probably could use physical therapy. So if you want to practice, let me know. Let's just touch on for a moment the next biopolymer, and that is the fatty acid. The fatty acid, or the fat lipid class, I guess. So fats, lipids, these are going to be typically, not always, but typically, their claim to fame is they're non-polar. So we got oils and things. We're not going to be making Jell-O with this stuff. They're non-polar. And the fatty acid has got a fairly basic structure. It's pretty easy to look at. The standard fatty acid that you're going to find in most living things, and that's really everything from bacteria on up to plants to you and I, we like 18 carbon fatty acids. As it turns out, there are fatty acid carbon numbers that are really common, and then there are carbon numbers that just don't exist. Why is that? I don't know. It just is the way it is. But 18 carbon, man, we got a lot of 18 carbon fatty acids. In the last moments here, this is how we draw fatty acid. So we have the carboxylic acid. This is carbon number 1. And now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. All right, so when you look in the book, various places anyway, they'll draw it as the line structure, but I think you miss out and you don't really get a sense of what it's doing unless you draw all the stupid carbons out. Now, we're going to add hydrogens in every possible spot. We're going to saturate this guy with hydrogens. And so that's why this is called a hydrocarbon, because it's pretty much see, this is what I'm saying? No PowerPoint, we're going to draw this. And you're going to say, why the hell are you doing this? It's like, well, look, there's 5 minutes left in class. There's no reason to get into anything too elaborate, but I can do this for a while. All right, good. And those of you at home, you can skip over that. Okay, so we have made an 18 carbon fatty acid. Now, remember we said that one of the cool things about organic chemistry is the predictability of it. We can actually make predictions about how this stuff is going to behave based on the number of carbons. And what I will tell you is, this is known in the chem biz world as steric acid. And you may know it as the wax and wax lips. Anybody know wax lips? A few, just so you know, a few nods. Do you know wax lips? A great Halloween treat. Stearic acid is pretty darn waxy. Now, the melting point can be controlled both by the number of carbons and by putting some double bonds in. Stearic acid, though, like if you take a can of coconut milk and crack it open, you'll see there's a layer of lipid, almost a wax at the top. That's a lot of stearic acid. You can get stearic acid from a lot of different plants and probably from animals. It is just a straight 18-carbon fatty acid. Now, you perhaps have heard about things like omega-3 fatty acids. This refers to the positioning of a double bond. And so, okay, if you haven't had organic chemistry, let's throw this out. When we put a double bond into this molecule, we're going to put one right here. You got a double bond here. First off, these two carbons have too many lines coming off of them because you can only have 4. They have too many bonds. And so you have to remove hydrogens. Now, because the carbon-carbon double bond, it's acting like a twin axle or something. I don't know what you think about it. But imagine you got 2 marshmallows and you stick a toothpick in between them and you can spin it. Okay. Now, if you take 2 toothpicks and stick it to the marshmallows, you can't spin one around the other. You spin both of them. And so when you have this orientation, it's actually fixed. So you can have the hydrogens on both sides, or put a double bond here, and we can have the hydrogens removed on opposite sides. And of course, this is known as the cis configuration, and this is the trans configuration. And I always remember this because cis, same side. Thank you very much. The trans configuration is this opposite sides. Now, because they're fixed in space, that is, they can't spin around, the orientation stays. And just another one of the quirks of biochemistry is anytime we got double bonds in fatty acids particularly, they are always in the cis configuration. That's just the way it is. Trans double bonds, we ain't got them. You just don't find them in naturally occurring fatty acids. So that's why there are certain fats that we can break down, and there are synthetic fats, trans fats, that we can't break down. And because it is at the very end of the class here, I can digress for a moment. In the past 15 years now, trans fats have been pretty much eliminated from our diet. I do, my label reading day in the food class where we get our Twinkies, and things still have some trans fats, but not a lot. Now, the reason this is an issue is that when you got double bonds present, the double bond, we can think of it as doing something like this, where it puts a kink into the fatty acid. And if you've got fatty acids like stearic acid that are just lined up straight, they're going to have a higher melting point. And the presence of double bonds lowers the melting point. So it turns out that stearic acid has got a melting point right around body temperature. But if you put in a double bond and say make an omega-3 fatty acid like a fish oil, it is no longer solid at room temperature, it's liquid at room temperature. So there are a lot of plant oils that are liquid at room temperature. And back, actually at the turn of the 20th century, this technology was developed, but it didn't get really rolling until probably around World War II. And that was the ability to take liquid oils that have a bunch of double bonds in them, that is referred to as being unsaturated fats, and putting them over a nickel or palladium catalyst and bubbling hydrogen through it, and you can add back hydrogens. You can begin to saturate it. So what you can do is take liquid oil, fully saturate it, and make stearic acid. Or you can partially hydrogenate it, and you can make a range of different kinds of things that will have melting points of really industrially exactly what temperature you want it to melt at. We can make it for you. And so you have things like margarines that are not going to be so hard that they tear your bread when you spread your butter out. Now, starting around 2005, the FDA and USDA begins limiting trans fats because since the 1950s, people had a pretty good idea that trans fats were leading to atherosclerosis and plaques in the arteries. So it takes, 55 years or so for it finally to make its way into public policy. But now we don't have any trans fats. Very few. I mean, you just don't see it. Which means that you don't have cottonseed oil and soybean oil partially hydrogenated to make a delicious cream filling. Because that is the whole, at least in my mind, one of the best advantages of using partially hydrogenated fats is the ability to make the cream filling. And if you read on your labels and things, like Oreo cookies, they have a cream filling. Hostess Twinkies are filled with a cream filling. But it's not CREAM, which is how you spell cream. It is KREEM, or God knows what, because it ain't cream. It's actually partially hydrogenated fat. That's enough. Thank you for your indulgence. All right. Oh my God, I talked for 51 minutes and 38 seconds.